Okay, so a couple things to hammer out, and we'll be mentally set up for what we need to discuss. So first, well, let's say this. What we're about to sort of phase back into thinking is in terms of position, velocity, acceleration. Position, where you are; velocity, how fast you're going; acceleration, how fast your speed is changing. Now, we saw when we were studying derivatives that if you take your position function and you compute a derivative, the slope of the position function will give you something not in meters, but in meters per second, change in y over change in x, and that gives you your velocity. And then take another derivative. Well, in particular here, this would be taking the derivative of the velocity function. You would get the slope of the velocity function, which is not meters per second, but meters per second, or meters per second squared. So we saw previously that taking derivative can get you from position to velocity to acceleration. But now, think about this. What derivative does, antiderivative undoes. So the antiderivative, or the integral, ought to take you from the acceleration function to the velocity function, or from the velocity function to the position function. And indeed, it does just that, and this makes mathematical sense. Now, before I get into I tell you what, let's just, rather than saying before I get into, let's just address that fact here. Because conceptually, it makes sense that what derivative does, antiderivative undoes, and if derivative takes you from position to velocity to acceleration, then antiderivative should take you in the opposite direction, from acceleration to velocity to position. Why does that make sense sort of in a more concrete way? Imagine, let's just say this was a velocity function here. Let's say every height of every rectangle was being measured in terms of meters per second, and every horizontal position measured in terms of seconds. Now, you know that you could discuss the area under this function, because hell, you could discuss the area under any function. And you know that that area would just be, well, some amount of space taken up by however much area is under the function. But here's the thing. This computation has physical meaning within the context of what vertical measures and what horizontal measures with respect to the parameters of interest. Horizontal, seconds; vertical, meters per second. So when you look at every rectangle, which would be capturing some amount of area, the height of each rectangle is in meters per second. Because this being the velocity function, the height of the function gives you information about the velocity. The width of each rectangle would be some chunk of the time axis, which would be some number of seconds. But now, when you compute the area would be some number of meters per second times some number of seconds. It would be just base times height times base. Well, the seconds cancel. And your area, then, whatever this comes out to be in terms of number, is going to be some number of meters. An area where the height is meters per second and the base is seconds, multiply together, the seconds cancel, and you end up with a meter. And this jives with what we said above. Above, we said derivative of position is velocity. Antiderivative of velocity is position. And in fact, that makes sense with respect to units. Take an area under the velocity function. You will no longer have a velocity unit. You'll have a distance unit. And, oh man, that's a huge realization. I tell you what, just to add more sort of salt to the fire, if you think about this, what is this computation ultimately going to be in terms of the position function? This is going to be S of B minus S of A. Well, because you know how to compute the area under a function, you find the antiderivative function and then subtract top bound minus bottom bound. Well, take the antiderivative function, that's the S function, is the antiderivative of velocity's position, and plug in the bounds. Cool. So, first order of business, what derivative does, antiderivative undoes, so position, velocity, acceleration are related by way of derivative, just as acceleration, velocity, and position are related by way of antiderivative. The units even check out when you run an integral. Cool. Let's address this last idea, because once we've got this, the table's set. So, displacement versus total distance traveled. These are two descriptive terms to describe two features related to motion. These are related to motion. Displacement only depends on two snapshots. Displacement only depends displacement only depends on two snapshots. Imagine this. By the way, total distance traveled, this is like an odometer reading. So when we talk about total distance traveled, it's how far you have gone in totality. Drive your car. It doesn't matter whether you're driving east, west, north, south, in any direction. This total distance traveled is accounting for how far you moved. Whereas displacement is just taking a snapshot of when you started, when you finished, and how far you went between those two snapshots. Let me give an example. Here's home, here's school. And on a given day, like at 8 a.m., you're maybe leaving the house. And 9 a.m., whenever you get to the campus, maybe at 5 p.m., you're heading back home, and by 6 p.m., you are home. Let's say 9 a.m., arrived to campus. Fine, okay, so here's your daily commute. Now, you could talk about the displacement between 8 a.m. and 9 a.m. Let's say, for the sake of argument, your commute it took an hour, let's say your commute was 40 miles. Okay, so your displacement between 8 a.m. and 9 a.m. is 40 miles. Why? Between the two snapshots, that's how far you went. Between 9 a.m. and 8 a.m., when you compare them, you went 40 miles. In fact, that is the same as the total distance traveled between 8 a.m. and 9 a.m. Because between 8 a.m. and 9 a.m., that's all the farther you went. But now, what is your displacement between 8 a.m. and 5 p.m.? Displacement only depends on two snapshots. Oh, how about 6 p.m.? Now this will be more interesting. Displacement only depends on two snapshots. It depends on where you started and where you finished. And at 8 a.m., you were home. And at 6 p.m., you were back home. So your displacement, you only have knowledge of where you were at 8 and where you were at 6. Your displacement is 0 miles. Whereas on the other hand, your total distance traveled is something else, because your total distance traveled between 8 a.m. and 6 p.m. is certainly not 0 miles. You went somewhere. In fact, you went all the way to campus and back. You went 80 miles. when you look at yourself and your own path of travel, between 2 a.m. and 2 a.m., your displacement is probably always 0, from bed to bed. But on any given day, my suspicion is your total distance traveled is more than that. You probably got out of bed and went somewhere. But when you think about displacement, all it measures is the initial time frame and the final time frame and taking the difference. Whereas total distance traveled is taking a continuous odometer reading, where no matter which way you travel, whether it's east or west, both east and west are going to be counted the same. Both north and south, or whichever directions that you travel, both to school and from school. So, between 8 a.m. and 6 p.m., displacement 0, because between 8 a.m. and 6 p.m., those 2 snapshots, you went nowhere. Take a snapshot at 8, take a snapshot at 6, the displacement between the 2 snapshots is 0. Total distance traveled 80. However, take the 2 snapshots like at 8 and 9, okay, fine. Your displacement was 40, your total distance traveled is 40. Cool. With displacement, total distance traveled, position, velocity, acceleration with respect to antiderivative, we're set up and ready to rock.